Gallium nitride is a binary 3V direct bandgap semiconductor commonly used in bright light-emitting diodes since the 1990s. The compound is a very hard material that has a Wurtzite crystal structure. Its wide bandgap of 3.4 eV affords it special properties for applications in optoelectronic, high-power and high-frequency devices. For example, GaN is the substrate which makes violet laser diodes possible, without use of nonlinear optical frequency doubling. Its sensitivity to ionizing radiation is low, making it a suitable material for solar cell arrays for satellites. Military and space applications could also benefit as devices have shown stability in radiation environments. Because GaN transistors can operate at much higher temperatures and work at much higher voltages than gallium arsenide transistors, they make ideal power amplifiers at microwave frequencies. Physical properties. GaN is a very hard, mechanically stable wide bandgap semiconductor material with high heat capacity and thermal conductivity. In its pure form it resists cracking and can be deposited in thin film on sapphire or silicon carbide, despite the mismatch in their lattice constants. GaN can be doped with silicon or with oxygen to N-type and with magnesium to P-type. However, the C and Mg atoms change the way the GaN crystals grow, introducing tensile stresses and making them brittle. Gallium nitride compounds also tend to have a high spatial defect frequency, on the order of 100 million to 10 billion defects per square centimeter. Developments. GaN with a high crystalline quality can be obtained by depositing a buffer layer at low temperatures. Such high-quality GaN led to the discovery of P-type GaN, PN-junction blue UV LEDs and room-temperature stimulated emission. This has led to the commercialization of high-performance blue LEDs and long-lifetime violet laser diodes, and to the development of nitride-based devices such as UV detectors and high-speed field effect transistors. High-brightness GaN light-emitting diodes completed the range of primary colors, and made applications such as daylight visible full-color LED displays, white LEDs and blue laser devices possible. The first GaN-based high-brightness LEDs were using a thin film of GaN deposited via MOCVD on sapphire. Other substrates used are zinc oxide, with lattice constant mismatch of only 2% and silicon carbide. Group 3 nitride semiconductors are in general recognized as one of the most promising semiconductor family for fabricating optical devices in the visible short wavelength and UV region. The very high breakdown voltages, high electron mobility and saturation velocity of GaN has also made it an ideal candidate for high power and high temperature microwave applications, as evidenced by its high Johnson's figure of merit. Potential markets for high-power high-frequency devices based on GaN include microwave radio frequency power amplifiers and high-voltage switching devices for power grids. A potential mass-market application for GaN-based RF transistors is as the microwave source for microwave ovens, replacing the magnetrons currently used. The large bandgap means that the performance of GaN transistors is maintained up to higher temperatures than silicon transistors. The first gallium nitride metal semiconductor field effect transistors were experimentally demonstrated in 1993 and they are being actively developed. In 2010 the first enhancement mode gallium nitride transistors became generally available. These devices were designed to replace power MOSFETs in applications where switching speed or power conversion efficiency is critical. These transistors, also called EGAN FETs, are built by growing a thin layer of GaN on top of a standard silicon wafer. This allows the EGAN FETs to maintain costs similar to silicon power MOSFETs but with the superior electrical performance of GaN. Applications: GaN-based violet laser diodes are used to read Blu-ray discs. When doped with a suitable transition metal such as manganese, GaN is a promising spintronics material. The mixture of GaN with in or out with a bandgap dependent on ratio of in or out to GaN allows the manufacture of light-emitting diodes with colors that can go from red to ultraviolet. GaN HEMTs have been offered commercially since 2006, and have found immediate use in various wireless infrastructure applications due to their high efficiency and high voltage operation. Second-generation technology with shorter gate lengths will be addressing higher-frequency telecom and aerospace applications. GaN-based MOSFET and MESFET transistors also offer many advantages in high-power electronics, especially in automotive and electric car applications. Nanotubes of GaN are proposed for applications in nanoscale electronics, optoelectronics and biochemical sensing applications. They are also useful in military electronics such as active electronically scan array radars. Saab's JAS-39 Gripen NG is using an electronic warfare system based on gallium nitride technology. GaN-based electronics has the potential to drastically cut energy consumption, not only in consumer applications but even for power transmission utilities. MIT spin-out Cambridge Electronics Incorporated's claim their transistors have at least 1/10 the resistance of such silicon-based transistors. This allows for much higher energy efficiency, and orders of magnitude faster switching frequency. This has huge implications not only for energy usage of power electronic systems, but their physical size and stability. Unlike silicon transistors which switch off due to power surges, GaN transistors are typically normally on. However, the company along with U.S. government and university assistants developed GaN transistors via materials engineering to be normally off just as silicon-based transistors. Synthesis equals bulk substrates equals GaN crystals can be grown from a molten Ga melt held under 100 atmospheres of pressure of N2 at 750 degrees Celsius. As Ga will not react with N2 below 1000 degrees Celsius, the powder must be made from something more reactive, usually in one of the following ways: 2 Ga plus 2 NH3 or 2 Ga N plus 3 hours 2, Ga 2O3 plus 2 NH3 or 2 Ga N plus 3 hours 2O. Equals molecular beam epitaxy equals, commercially, GaN crystals can be grown using molecular beam epitaxy. This process can be further modified to reduce dislocation densities. First, an ion beam is applied to the growth surface in order to create nanoscale roughness. Then, the surface is polished. This process takes place in a vacuum. Safety: GaN dust is an irritant to skin, eyes and lungs. The environment, health and safety aspects of gallium nitride sources and industrial hygiene monitoring studies of MOVPE sources have been reported recently in a review. Bulk GaN is non-toxic and biocompatible, and therefore may be used in the electrodes and electronics of implants in living organisms. See also, Schottky diode, semiconductor devices, molecular beam epitaxy, epitaxy. References. External links: IOF Data Archive.